Dear all, in continuation to my lecture series of normalization, today I'm going to discuss with you the lossless joint decomposition and dependency preserving decomposition. Right. So before we start of the topic, first we should know what is the need of this lossless joint and dependency preserving decomposition. Right. So decomposition of a relation is done when a relation in relational model is not in appropriate form. So to make it in appropriate form, we just normalize a relation second, third, fourth, and fifth normal. After the decomposition, what happened? We just get a few relations from the main relation, and now the question arises: is that decomposition a lossless or dependency preserving decomposition? Because if see, when we just decompose a relation, then two things are important. The first thing is there should not loss, or in other way we can say that two things we should take care. The first thing is, if in a relation, suppose there are number of attributes 5, and when we decompose the relation, then in decomposition part, the total number of attributes should be 5. That should be there in a decomposition relation, and there should not lose any single attribute. And the second thing is the relationship between different attributes in a relation that should also maintain. So this we will discuss in dependency preserving decomposition, right? So these are the two important properties of the decomposition. The first is the lossless joint decomposition, and the second one is the dependency preserving. So in this lecture, I'm going to discuss with you how to check the lossless joint decomposition. So I hope all of you are able to understand the method to check the lossless decomposition, right? See, what happened if this is the question, like consider the relation R, A, B, C, D, E, F, G, H, and suppose the following FDs hold. F, A determine B, C, and this. State whether the following decomposition of relation R is lossless joint decomposition or lossy, right? So these are the three relations R1, R2, and R3. Now what you have to do, you have to check, is this lossless or not? So the first method is just count how many attributes in the relation. So in this relation, the total number of attributes are 1, 2, 3, 4, 5, 6, 7, 8. 8 attributes. So just what you can do, just write like this: A, B, C, D, E, F, G, H. That means just make a matrix, and in that matrix the number of column is the number of attribute in the relation. So there are A, B, C, D, E, F, G, H are the different attributes. So just make 8 column over there like this one. Now how many rows over there? See here, there are 3 decomposition, the 1, 2, and 3, R1, R2, and R3. Then what you can do, you can just make a 3 decomposition over here like this one, 3 decomposition, R1, R2, and R3, right? Now write R1, R2, R3 in this place like this one. This is R1, R1, this is R2, and this is R3. So I hope all of you understand up to this. Now what to do? See, in decomposition R1, A, B, D, F over there, right? So in decomposition R1, in the place of A, B, D, F, write small a, B, D, F, write small a. In R2, A, C, D, E, G, A, C, D, E, G, right? A over there. In R3, A, G, H, A, G, H, A over there. And in rest all places, put B. And in rest all places, put B, right? Now, what you have to do, with the help of all these FD, try to make A in any one row. Whenever you get all A in any one row, then just write, yes, this decomposition is lossless decomposition, right? Now, what is the method? Like, see, first come through this FD, A determine BC, A determine BC. Now, in the column of A, see, where is the pair of A? So, if in the column of A, you just see the pair of A is this one, right? You can also take the pair of A like this one. You can also take this one. You can also take this one. So not necessarily if first you just take this one and that one. Any one of them, you have to take the pair of A, right? In corresponding to A, like here, A determine BC over there. In corresponding to A, in B and C, if B is there, then just cut B, like in C, this C, B is there, just cut it and write A. Similar over here, cut just this B and write A over here. So A determine BC, it did over there. Now come to this pair, in this pair. In corresponding to this pair, A determine B, yes, already cut it. And in this line, this is BB. So A determine BC is there. So you can simply cut this A and cut this A, right? Now see the second FD, F determine A. Now for F determine A, when you are going to check for F determine A, see in F, there is no pair of A. No pair of A. So don't need to do anything. Now see, in CD determine E. So when you check for FD, CD determine E, CD, C pair of A. Yes, in CD, this is the pair of A, this is the pair of A. See, a pair of A, this one, but CD on the left hand side, then in C or D, all A must be there. All A must be there. If any one of them is B, then don't cut this B in corresponding to CD, right? So 4A over there, CD is there, na? So pair of A you are talking about, so just take these 4A, right? In corresponding to this, CD determine CD. This cut this B and write A. This is already okay. Now see, you cannot take this pair. Why not take this pair? Because this A is okay, this A is okay, but this B create a problem. So you cannot take this pair, right? Now, for the another FD, B determine D. So when you just consider the B determine D, in B, just take this pair of in B, this pair of A. And in D, D already A is there, so no need to do anything. Now when you take the pair of A in B of this one, then in corresponding to this D, in D, yes, this B is there. So just cut it and write A. So already, right? And for the FD, A determine FGH. Now what happened? A determine, just take the pair of A determine FGH. FG, so this cut A, this cut A. Cut A and this cut A. Because A determine FGH. So cut B and write A, cut B and write B. And when you take this pair of A, then is corresponding to this A. So what happened? This row consists all A. So whenever any row consists all A, just stop there and write about decomposition. About decomposition is lossless decomposition. So I hope all of you understand this method. Now let us discuss the second method. See how many attributes in this? A, B, C, D, E, F, right? A, B, C, D, E, F. A, B, C, D, E, F, and G and H. Right, so these are the attributes. So just count all attribute 1 2 3 4 5 6 7 8. That means 8 column over there, right? So 8 column you already write like this. Now how many row in this matrix? The number of row in this matrix are the number of decomposition, right? So how many number of decomposition? There are 3 number of decomposition. The number of decomposition is R1, R2 and R3. So there are 3 decomposition over there, like this one, R1, R2 and R1, R2, and R3, right? So we can write over here R1, R2, and R3. Now do the same practice as we discussed in the previous example. In previous example, what we discussed, A, B, C, D. Put A on the place of A, B, C, D. In R2, A, B, C, E, and F. A, B, C, E, F, right? And in R3, A, D, F, G, H. A, D, F, G, H. Right? Now what you have to do? The next is on the rest all places put B. On the rest all places put B. On the rest all places put B. Like this one, put B, like this one, put B, and put B like this one. Now come to each FD. See, first, when you come through AB determines C, then what happened? In AB, yes, AB, pair of A is there, pair of A is there. So this is the pair of A, AB, AB determines C. So C, just cut it and write A. This pair you can't take. Why can't take this pair? Because this A, this B is create a problem over there. So can't take this pair, right? Okay. BC determine D. Now for the second FD, BC determine D. BC AA take. D is there. Okay. We can't take this pair because B is there. And E determine F. In E, there is no pair of A. No pair of A. So no need to change anything. Now G determine F. So in G determine F, what happened? In G, again in G, there is no pair of A. Again in G, there is no pair of A, right? Yes, no pair of A. And H determine A. In H, there is no pair of A, right? In FG, there is no pair of A. In FG, there is no pair of A. So simple here, it is not possible to make all A in a row, right? Let me check again. Mm, yes, this is not possible. So here we can write this decomposition is no lossless, no lossless. Or in other words, we can also write is lossy decomposition. Because what happened, now it is not possible to make all A in any row. So simple we can write this is lossy decomposition, right? Now come to the third question. Now, see in this question, how many attributes? 1, 2, 3, 4, 5. So in relation are 5 attributes: V, W, X, Y, and Z, right? So just make a column like this, right? And the decomposition is only 2, right? The composition is only 2. So this is R1 and this is R2, right? In R1, VWX. So write A in the place of VWX. In R2, VYZ, VY and Z. And in rest places, put B. Now see from the FD, Z determine V. In Z, there is no pair of A. W determine Y, no pair of A. XY, no pair of A. And V. And in V, yes, pair of A. V determine WX. V determine WX, yes. And A and A. So what happened here? All one row contain all A. So here you can write, yes, this is lossless decomposition. Lossless